All right, welcome. In this video, we're going to talk about page 17, some bronsted lowry and acid-base properties practice. And I want to point out that I'm making this video that's directly about this page, but there's also some videos up here at the top that are helpful, just more about acid-base in general. So there's a crash course video. Those can be kind of fun to watch, just about acids and bases, and it covers some of the stuff we'll talk about here with bronsted lowry. And then here's an example of me talking through how to write these bronsted lowry acid-base reactions here. So there's these two video links to look at as well. But I wanted to make this one to talk through a few specific things on this page. So on the top here, we've got just some practice identifying properties of acids and bases. So this is something that we could pick up from either our experience in the lab and also the reading that we did. There is some reading about properties of acids and bases. This has a lot of good information in it. So let's go back to where we were here. Okay, so I made a slide here summarizing some of the key things from the reading. So one thing that acids have in common, they have a sour taste. So this is an example of something that's an acid. Bases tend to have a bitter taste. If you think about what we mean by sour, like, citrus fruits, an example is something that's acidic. So think like lemons when we're talking sour taste. We also know that that acids make hydrogen ions. That's part of one of our acid-base definitions. And we had another reading on that from last week. So what makes an acid is that when you stick it in water, it makes hydrogen ions. So that is a property of an acid. Electrolyte, I don't know if this one got covered in there. But these substances are both electrolytes. They both conduct electricity. And the reason why they are electrolytes is because they form ions. So anything that forms ions will conduct electricity. And so acids make hydrogen ions, bases make hydroxide ions. Things that feel slippery, that would be bases. So if you think about soap, or if you've ever accidentally gotten like bleach on your hands, it will feel slippery. Don't do that, it's not good for you. But that feeling slippery is a characteristic of bases. Corrosive, both acids and bases are corrosive, meaning they can, damage your skin or other substances. So bases produce hydroxide ions. Both acids and bases can be detected using an indicator. We've used both universal indicator and cabbage juice in class as examples. Soaps are an example of bases. So a lot of bases are cleaning products. A lot of common cleaning products like bleach and soap and, Windex has ammonia in it, which is a base. So those are all examples of bases. Another definition of acids, we say that acids make hydrogen ions. And when you stick a hydrogen ion in water, they actually stick together and form this thing right here, H3O+, which we call hydronium. So that's another way we can use to describe these hydrogen ions, is we can call them hydronium ions. So that's another way of thinking about what acids do. Both acids and bases exist in aqueous solutions. So whenever we define acids and bases, we're thinking about what they do when we dissolve them in water. So they either make hydrogen ions when we dissolve them in water, or they make hydroxide when we dissolve them in water. HCl is an example of an acid. Something you'll notice about the acids, they tend to start with a hydrogen. So for example, HCl, HNO3, H2SO4, those are all examples of acids. Ammonia is a base, and this is something that we saw in the lab. That was one of the common substances. Ammonia is found in some cleaners, like you might be able to just kind of buy a bottle of ammonia, or something like, the classic Windex has ammonia in it. pH greater than 7, those are bases. pH less than 7, those are acids. And then water is an example of something that is neutral. I guess you can think of it as being both an acid and a base. So what happens with water, actually, as a little aside here, is that when water, a little bit of your water in like your glass of water that you're drinking will actually break apart and form hydrogen and hydroxide ions. So it is kind of equally acidic and basic, which is what makes water neutral. So when it breaks apart, it makes equal amount of hydrogen and hydroxide ions. So that's a fun FYI there. Okay. The other thing that I wanted to talk about is, so some of these kind of refer back to the reading. So look back at your reading about what makes a weak acid versus a strong acid. There's some pictures of these in the readings from last week. I'll give you a hint. Strong acid totally splits apart into ions, whereas weak acids, only a few of them break apart and form ions. 19 is asking you to draw a pH scale. So what we mean there is like, this is what we mean by that. Whoops, I mislabeled that. So if you make a number line, 0, 7, 14, and place these along a number line, look back to your lab data from last week. So if something turns universal indicator purple, look back at your lab from last week and ask yourself, okay, what did that mean? So the lab from last week, that was page 12, exploring acids and bases. So we're kind of doing something similar to this, making a number line. And remember, we have this color chart right here on page 12 that you can refer to. You might even want to snip it. I might actually do this right now. I'm going to snip it and paste it over here on this page for you. Okay. Alrighty. So these practice problems down here are using that Bronsted-Lowry definition of acids and bases. And what I'm talking about here is, if we go back to page 13, our acid-base theories, we looked at this last week. Let me scroll down here. The Bronsted-Lowry definition of acids and bases is, we think of acids as being hydrogen givers and bases as being hydrogen takers. So I'm going to go and I'm also going to snip this and paste it over here. And so let's take a look at what we mean here. So in this example from the reading, we can see how ammonia can be a base. So we know that bases add hydroxide ions to solution. And so you might look at this chemical equation NH3 and say, well, how could this give hydroxide? I don't see any oxygens in ammonia. That seems impossible, right? What happens is when you stick ammonia in water, it actually behaves as a hydrogen taker. So a base is a substance that can accept a proton. And by proton, we mean a hydrogen ion. So a base is a hydrogen, whereas an acid is a hydrogen giver. And sometimes we use this technique to remember which is which. So if you think bad, it is bases accept hydrogens, and then acids donate. So bases are hydrogen takers, acids are hydrogen givers. So if we look down here at this example, we can see how that works. So if you stick NH3, ammonia, in water, what happens is ammonia is a base, so it is a hydrogen taker. So it's going to take a hydrogen from water. When it does that, NH3 becomes NH4 now, and then your H2O is now OH minus. It took one hydrogen away, right? So now it's just one hydrogen and oxygen. So we can see how we made a hydroxide ion, even though this substance doesn't have any hydroxide in it. So you make a hydroxide ion by taking a hydrogen from water. And that's how some of these bases work. And this we sometimes refer to as like a Bronsted-Lowry reaction. We're showing what's going on when you put the substance in water. It's either giving a hydrogen or taking a hydrogen. And yeah, so we want to do some practice with this over here. So first we want to identify whether something's an acid or base based on the reaction that's given. So in this case, we got water and HCN. And if we look at what happens afterwards, it looks like HCN lost a hydrogen and became CN minus. I like to kind of draw in an arrow to show what's going on, right? This lost a hydrogen and then H2O gained a hydrogen. And so remember, if something's a hydrogen giver, that means it's an acid. So this one gave a hydrogen. And that means water's a hydrogen taker, so it is behaving as a base. hydrogen taker. Okay. Over here, looks like our CO3 became HCO3. So in this case, the CO3 took the hydrogen from water. So the CO3 is being a hydrogen taker. So that means the CO3 is acting as a base, and your H2O is acting as an acid. So this, again, the base is your hydrogen taker. This one is your hydrogen giver. You'll also notice that when you put the base in water, it makes hydroxide ions. Okay. When you put the acid in water, it makes these H3O plus ions. All right, and if you look at our last one here, whoops, there's actually a typo on this one. I'll have to fix it. This should be HSO4. Okay. And it becomes H2SO4. So it's a hydrogen taker. So that means this is acting as a base. Notice how it makes hydroxides. It also makes sense it's a base, because when you stick it in water, it makes hydroxide ions. And in this case, water is behaving as an acid. It's being a hydrogen giver. So you can see, we said earlier that water can kind of act as an acid and a base. So when we say water is neutral, it's kind of equally good at being an acid and a base, and it can act as either in these situations here. And so down here, this is more independent practice, so try it on your own. There's some reminders here. When you're trying to predict the products here, this is one of the most straightforward reactions that we'll do, because the only thing that happens in this type of reaction is a hydrogen moves from one substance to the other substance. That's it. And it's only ever one hydrogen. That's it. So like in this case, we say H2CO3, it's an acid. An acid, what will acids do? They're going to give one hydrogen to water. So it's going to give one hydrogen to water. Okay, so H2CO3 becomes HCO3, and then H2O becomes H3O. And then we want to pay attention to charge. This hydrogen has a +1 charge. So if I gain a hydrogen, I become more positive. If I lose a hydrogen, so I started out neutral, I lost a hydrogen, now I'm negative here. Okay, let's look at one more example. Let's look at a base. So a base is a hydrogen taker. So what a base will do, it will take one hydrogen from water. So ClO4 becomes HClO4, and then H2O becomes just HO, which we more often write as OH. And remember that hydrogen that's moving has a positive charge. So if I start -1 and I add a +1, now I'm neutral. So this one's going to be neutral. And this one starts neutral and it loses a positive. So now this one ends up being negative. So that's how we would write reactions like this one. All right, so give these bottom few a try and send me, chat message if you have any questions.